neutrinos?
So neutrinos are sort of like these very light, like less massive versions of electrons that don't have an electric charge. And that makes them really interesting to study because, for one, they're hard to detect, and two, they are also the only particle in the standard model, which is the collection of the table that collects all the fundamental particles that we know of so far, that only interact via the weak force.
Okay.
So
And how unique are neutrinos? Because in your dissertation you say they're fundamental, but they're also very hard to study.
yes, so in the sense, well, they're unique in the sense that everything else in the standard model that makes up matter, so all the fermions in the standard model are charged particles. So the techniques you use to detect them, like basically when a charged particle exists and it moves through a magnetic field, it bends. When it goes through something that it can be ionized, it ionizes. So that's why we talk about ionizing radiation a lot. And you can measure the effects of this ionization process.
Can you give an example?
Yeah, so for us, we're using liquid xenon as a medium. So xenon, the noble gas, we condense it into
Isn't
a
that
liquid.
54 on the periodic element?
Yes, it is element 54. And we have a bunch of liquid xenon, and essentially any charged particle that passes through the xenon ionizes it and causes it to glow, and it glow in a very specific way. And that's called scintillation light, and we measure that scintillation light as well as the kind of ionization track that's left behind. And combining those two things, you can reconstruct what type of nuclear decay happened.
Okay, so it sounds like you're studying particle physics, given how in depth you are with the specific particles right now.
Yeah, so it's pretty much the thesis, or my focus has been, I would say, particle astrophysics. It's been a mix of like 3 different fields. For example, this double beta decay process is a nuclear physics process, but we're exploring it to do particle physics experiments, so measurements that tell us about the particles themselves, in this case, neutrinos.
And there's something that you mentioned earlier, which was charged particles.
Yeah.
Is it possible for a particle to not be charged?
Yeah, so neutrinos are uncharged.
Oh.
So as soon as they're born, they basically travel in a straight line, for as far as we can tell, forever until they interact with another particle and somehow emit some charged particle in some process.
Okay.
And so what we actually can measure is the result of that.
Oh.
So we measure the charged particle that's emitted in the end, which you can either think of as the neutrino being converted into the other particle or as another particle being emitted.
Okay. And it is established that neutrinos go beyond the standard model. And I was wondering if you could... Yeah, go ahead.
Yeah, so it's not that neutrinos go beyond the standard model. It's that the fact that they have masses, it's not obvious how to account for that in the standard model.
Can you explain further?
Sure. So the way we think particles, fundamental particles, have their masses come about is through what's called the Higgs mechanism. And the Higgs mechanism, in short, is a way to kind of marry the left-handed and right-handed components of various fields.
Okay.
And when you do that, you actually intrinsically gain a mass for that particle based on how strongly it couples to the Higgs field. So it's like a three interaction term where you have the Higgs and you have the right and left components of the fields, and they're all glued together. The neutrinos, only the left-handed components can interact with the weak force. The weak force completely breaks this left-right symmetry.
Okay.
And so you either have to admit a right-handed neutrino field, which we know we will not measure, at least through the weak force, and since it doesn't have an electric charge or doesn't interact through the strong force, there's nothing we can do to measure them. So you have to just hypothesize that these exist and then marry them to the left-handed components, and then you can get a mass this way. Or you have to think of some other mechanism to generate the neutrino masses.
Okay. And how important is symmetry in physics? And why is it important that neutrinos they're not anti-symmetric, but they don't work exactly with these symmetrical laws?
So, I mean, symmetries in physics, it's very important. They're very important. But what you're asking about is neutrinos right now?
Yeah.
So could you repeat that question? Because I got sidetracked there
That's
for
okay.
a second.
So obviously symmetry is extremely like fundamental to physics, and you're saying neutrinos do not interact symmetrically, correct?
Yeah, but the types of symmetries we're thinking of are different, I think.
Okay.
So this kind of left-right handedness symmetry is a discrete, like it's like kind of like a reflection in a mirror. But there are more, there are many continuous symmetries um, that are associated with conservation laws through this thing called Noether's theorem, which is
Know this theorem.
no, I wish it was Noether's theorem. Noether's, so it's
Okay.
Emmy Noether. She was a mathematician back in the early 1900s. Wrote down this theorem that essentially shows that for symmetries of this mathematical object you can construct called the action of any physical system you can think about, any symmetries associated with the action have to be correspondingly associated with some conservation rule.
Okay.
So in that sense, symmetries are very important in physics, because if you notice a symmetry in your action, then you know that there has to be some mathematical object that is conserved throughout the processes that will occur in that system. Does
Okay.
that make sense?
Yeah, it does make sense. So, what don't we actually understand about neutrinos then?
We don't understand how they have their masses. We know that they have masses, and we don't know what mechanism by which they generate them.
Okay. And what is a
That's-
mass in this instance, actually?
Mass is kind of your resistance to motion in a sense. So this is like, the way I'm thinking about it is inertial mass, but there's also gravitational mass. And, you know, if you have this property that's, if it's large enough, you end up bending, you know, your space
Time.
time. But that's not neutrinos. Neutrinos are extremely light, and also all these fundamental particles are extremely light that you can basically treat the space in which they're operating in as completely flat.
Right, like
They're-
of the atoms themselves.
So mass in this sense is just like it's a tool that we can use to be able to show how like the dynamics of a system will evolve
Okay.
from an inertial perspective. So something heavy will continue moving in a straight line if it's very heavy compared to a light thing that knocks it, for example.
Right.
Yeah.
So what you're saying is that what we don't know is how they get their masses, essentially.
Yeah.
And what's the hypothesis around as to why they might have their masses?
So I can tell you how we know they have masses.
Yeah.
Okay, I will draw this on this piece of paper, but eventually
We will digitize it afterwards.
We'll digitize it afterwards. But you basically have a situation where each neutrino is associated with another particle, okay, which is called a lepton. So an electron is the lightest one of these. An electron is charged, and so is the muon and the tau particle. And there are 3 neutrinos, one associated with each of them.
Okay.
When you have a particle physics process that occurs, so some interaction occurs, and you convert in some sense between these two states, between the neutrino state and the charged particle state, for example, you create neutrinos in what's called a flavor eigenbasis. So in one of the flavor eigenbases. And what that means is like, these are 3 different flavors here, 1, 2, and 3. And when a neutrino is born, it's born as one of them. Okay?
What do you mean by born?
When a neutrino just pops into existence from some other physical process.
Do we know how that process occurs or no?
Yeah, there are many processes that can emit neutrinos.
Okay.
So like in the same way that like you can have something hot emits like photons, like it glows red.
Or like these lights, I guess?
Or these lights, yeah, this is like a chemical process emitting photons. Yeah, so that's, you know, that's an electromagnetic process.
Right.
So weak interaction processes can emit neutrinos.
Okay. And
Okay.
what are examples of weak processes? Forgot the middle word.
So, well, that's just anything that is mediated by those bosons you have on the table over there, which are, which is a funny term to call them, but essentially they're these other particles called the W and Z bosons, and there's 3 of them. There's a charged W, so it has a positive and negative charge, and then you have the Z boson, which is like a neutral particle. These things are heavy, and when you construct like an interaction but you still have to obey all the rest of the symmetries of the standard model, there are certain processes that are allowed to occur. So the case I'm thinking about is like when you convert between a neutron to a proton in your nucleus, like going back to our beta decay example. If you convert between a neutron to a proton, you have to conserve charge, so you have to also emit an electron. Because protons and electrons have opposite charges, and this has a charge of 0, the neutron has a charge of 0, and that's cool. Now, but you also have to conserve something else called lepton number, which is associated with these neutrinos. Because an electron is part of this lepton family, so you can't just have it show up out of existence, out of nowhere. So you also have to emit an anti-electron neutrino. So this is how an example of how a neutrino
Which is like
born.
antimatter, right?
Which is a version of antimatter, yeah.
Okay.
And this is an example of how a neutrino can be born. So now that it's born in this flavor state, this electron type. But as it moves through space and flying through space, you can detect it sometime later by the reverse of this process, for example. And when you do that, you either emit a muon, a tau, or an electron with some probability.
Some probability.
Some probability, which we can calculate.
Is it random, or is there a specific number to it that's like consistently reoccurring?
It's random in like, it's consistently reoccurring as a function of energy and distance traveled.
Okay.
But it's not random in the sense that it's just some random probability. It's like, okay, the chances of it being an electron is 1/3 at this distance and this energy. But if you move slightly further, the chances of it being an electron is like 1/4. So the whole total probability sums to 1, or at least we hope so.
Okay.
Unless there are other types of neutrinos that we're unaware of.
Okay. So then if we understand how they gain their masses, what does that exactly reveal to us about, I guess, particle physics / astrophysics, since this is happening in space, correct?
Yeah, this is happening everywhere.
Everywhere, okay.
Yeah, it's not really revealing to us that, well, one thing that's interesting is if we do know how they generate their masses, for example, the experiment we're trying to look for this thing called neutrinoless double beta decay. So if you have this exact process, this neutron to proton conversion, and instead I have 2 neutrons converting to 2 protons plus 2 electrons, and I don't emit neutrinos, right?
Right.
For some reason, you can imagine that these 2 neutrinos are antiparticles of each other, and they annihilate within the nucleus. This is one way to imagine this occurring. If this happens, then you know that lepton number, which is one of those conservation rules, is not conserved.
Okay.
So suddenly you're in a situation where you've created more leptons than anti-leptons from a physical process. And so now you can imagine how this relates to like the whole like matter-antimatter symmetry problem. It's a much deeper hole to actually get there.
Right.
It's not as simple as, the matter-antimatter problem is not solved by saying these decays occur in the early universe. That's not what's happening.
Okay.
But this allows other physical processes to occur that do not conserve lepton number as well. It means it's possible. And the reason that's interesting is because there's no symmetry that's actually imposed on the standard model that tells us that lepton number needs to be conserved. It seems to be conserved as far as we can tell. So in that sense, that's why it's very interesting to me. It's like this is an accidental symmetry is what people call it.
Okay.
It's that it's not coming from some underlying kind of there's no underlying system. Yeah, there's no underlying symmetry of your system that tells you that lepton number is a conserved variable across physical processes. It just so happens so far.
Okay, and how common are these, I guess, dead ends in physics in general? If it's appropriate to call it a dead end.
What do you mean by dead end?
Well, as in you said that there's no real formula to really establish this loss of conservation.
As far as I know, there isn't like a symmetry that leads to lepton number conservation.
Right.
Which is why I think it's interesting to test.
Okay.
Because, you don't have to know that certain symmetries give you conservation laws, But you know that if you have conservation laws, then you have to have some symmetry. You don't have to have, well, actually, you might have to have one. But anyways, my point is we don't know what the symmetry is, so we don't end up with the conservation rule associated with it. We just seem to observe the conservation rule. And that's part of what physics is, right? A lot of it is just observing the world and seeing how it works and then saying, okay, this is how the world works. Can we explain why it works this way?
And when you say the world, do you mean on Earth or in space or both?
Both. I mean, from the perspective that I'm talking about the world, I'm assuming that the physics is the same across the universe.
Right.
That's not necessarily something that everyone agrees with, but there's very few arguments for why it wouldn't be the same across the universe, and they're pretty on the fringes of physics today, I think. But I think it was Dirac who did actually postulate that maybe physics does change over time. For example, the fundamental constants of nature are not fixed, versus in the framework that I'm explaining to you right now, like the electron's charge, for example, is the same now and it will be the same in the future, and it has been the same in the past.
Okay.
Yeah.
Can you go more on this lack of fundamental change in nature, or the reverse, excuse me?
What do you mean?
Like the theory you just postulated.
Well, it's not, I don't really know much about it.
All
I know is that Dirac has postulated this, and there are papers written about this, and as far as I'm concerned, if there are ways to test this, then it's interesting, and if it's not testable, then it's not really physics.
That's
if
fair.
you're just playing around with mathematical models, it's like, that's cool, but that's mathematics.
Yeah, I would agree with that.
Yeah.
You also mentioned earlier that there was an antimatter and matter symmetry problem. Could you go more into that?
Yeah, so for every particle we have in the standard model, so that includes electrons, protons, neutrons, protons, neutrons aren't part of this, the quarks that are making up protons and neutrons, plus electrons, muons, and tau particles, these things I just drew over here. You have an antimatter version where you take all the quantum numbers and you flip them, and you end up with the same particle, same mass, everything's the same except all the charges are flipped. The scenario we can think of most obviously is electric charge. So you have an electron, you flip its charge, you end up with a positron, which is an anti-electron. Okay, and these exist, and that's how PET scans work, actually. We measure positrons annihilating with electrons in cancer. And when you do that, you can reconstruct where that annihilation happens, and that's how you detect where cancers are. Anyway, so this is a real thing. What I will say is that the world we live in today, if you look around, the vast majority of all particles we have around are made up of regular matter. Like 1 in 10 to the 9, I think. So which is 1 in a billion particles that are just kind of in existence are antimatter particles. And we don't know why this is the case. We don't know why there's such a huge bias on one side of this. When physical processes, as far as we can tell, tend to conserve either the number of matter particles or the number of antimatter particles in any system. That's the matter-antimatter symmetry problem in short.
And what are the proposed, if you know, obviously, what are the proposed solutions to this problem?
There are many proposed solutions. I mean, now you're getting into the realm of cosmology, which is the study of the universe as a whole, and the history of the universe. And Sakharov in the 60s, I think, proposed 3 axioms that basically said, for you to dynamically create an asymmetry between matter and antimatter, you have 3 conditions that need to be met. First, you need to not conserve baryon number, which is the number of baryons, and these are a class of particles. So that has to not be an actual valid conservation rule. The second is that the system you're in needs to be in a non-equilibrium state. So you can't have a thermal bath where it's just everything is just stable. You have to have some non-equilibrium state. And the third is that you have this combination of discrete symmetries, which is charge and parity. So that parity is this mirror reflection thing, the right and left-handedness. Charge is like electric charge, for example. And the combination of the two needs to not be conserved as well in some processes. So if you have all these 3 conditions met, there's a way to generate an antimatter-matter asymmetry between the two. Now, that's not necessarily saying that that's the solution, because there's no mechanism to do this right now, or there's no mechanism that's kind of at the forefront. But one way is people talk about is called leptogenesis, which is kind of related to this double beta decay process in some sense, which is if you have a situation to generate neutrino masses that doesn't require there to be these kind of right-handed neutrino fields, and you can actually, you have the right-handed neutrino fields, but there's something that allows you to couple only the left-handed fields to each other or only the right-handed fields to each other. Then, if these things are really heavy, and they existed in the early universe when things were very hot, and like when things are very hot, energies are high. When energies are high, you can generate more massive things. But then the universe is expanding rapidly. And as the universe expands, it cools. And at some point, the kind of forward and backward process of creating these heavy particles, you kind of only allow them to decay. But because you can't generate them anymore because the temperature has dropped enough. And if you allow them to decay using some fancy like selection rules in like particle physics and kind of obeying the symmetries of the standard model, you can sort of maybe see a pathway for how this happens. Anyways, like this is a very brief summary, but like the mechanism that I'm referring to is called leptogenesis, or the class of mechanisms I'm referring to are called leptogenesis.
Or section 2.3.2 in your thesis as well.
Yes. Yeah, I tried to briefly go over it there because I think that's an interesting connection between like, essentially what we're doing is we're just looking for a hypothetical form of decay, but it's actually connected in a very real sense to if we see this decay, then there's a pathway to explain the matter-antimatter problem, which is a cosmology problem, using this nuclear decay, which we're actually doing to try to understand something about this particle called the neutrino. So like the way physics is connected between different domains in some sense is super interesting to me, and I think it's worth like highlighting.
I agree. So I have two like follow-up questions. The first one being, are there anti-neutrinos, and do they behave in exactly the converse or reverse of neutrinos?
There are anti-neutrinos in the sense that like when they interact, when we see some neutrinos interact, they produce antimatter particles instead of regular matter. So this thing that's emitted over here in this double beta decay process is an anti-neutrino because it comes out at the same time as a regular electron. So you have to kind of cancel out the matter-antimatter in this situation, right? Whether they interact exactly the same as regular neutrinos, we don't know, and that's actually part of the ongoing like big global neutrino physics program is trying to understand this. So these are the general class of experiments are called like neutrino oscillation experiments, and the big ones that I can think of that are coming online or are online are like Dune, Hyper-K, and the Juno experiment are the three like next gen.
And where are these being done?
So Dune is going to be based in the US at Fermilab, which is I think near Chicago.
Okay.
Hyper-K is in Japan, near Kamioka. And Juno is somewhere in China, in Jinping, I think. And yeah, they're all pretty much using different experimental techniques to try to see if regular neutrinos and anti-neutrinos oscillate in different ways, or they oscillate in exactly the same way.
And do you know the results right now, or is it still like a huge...
No, this is an open question. So this is like people are working on building these experiments. Yeah.
And you also mentioned that neutrinos play a significant role in the early universe, as did heat. What is their role exactly?
Well, in the sense of, so neutrinos are super duper light, like I said, right? So the energy kind of barrier you need to create them is quite small. The other thing is neutrinos don't have an electric charge. So the way they interact with like other stuff in the early universe is different than things that are charged, number one. And number two is that as the universe cools, you go from particles behaving in a relativistic manner because they're super, but when things are really hot, things have high energy. If that energy is about the same order of their mass through this like E equals mc squared, then you would say the particle is relativistic, which means the kind of mechanics that it undergoes is like you don't treat it as a classical physics
Mhm.
problem anymore.
Is that why it's beyond the standard model?
No, that's all within the standard model.
Oh,
that's
okay.
that's not
Okay.
anything fancy. That's like special relativity, like
Okay.
yeah, Einstein 1905.
Okay.
um,
Oh, it's over 100 years ago.
yeah, it is over. It's crazy. But what neutrinos do in the early universe is essentially like as the universe cools, most particles become non-relativistic at some point, and neutrinos stay relativistic for a bit longer. So now you have this soup of photons, like regular light, and neutrinos, and there's so many of them, and the neutrinos do have mass, as we know, so they actually start to smear out of the clumping of matter. And depending on how quickly the universe's temperature drops, the mass of the neutrino, et cetera, you can sort of try to imagine like the universe is trying to clump together, but you have these neutrinos that are massive that are kind of smearing that out. So instead of having larger clumps, you kind of
They space
Small.
out, I guess.
yeah, they space out. So I believe this is not my area of expertise, so like everything I say with a grain of salt. But I think you start smearing out like small scale structure formation, so like smaller clumps rather than larger ones, depending on how many neutrinos you have and also the energies at which they're moving relative to the universe's expansion, something like that.
And do they keep their energy levels kind of the same when everything cools off because they're so light?
No, they actually get, so when we observe them, like you have things in the universe are rapidly moving away from us, right? The further and further you look.
Well, aren't we moving as well?
Yes, but like the distance like between us
Mm-hmm.
is actually quite close on a cosmic scale. So we don't actually notice this. But and also there are other forces that are keeping us together. Like the Earth is a massive gravitational body that's attracting us. But when you look at cosmic distances and you try to see, well, you can see this with light. When you look at things further away, they get redshifted.
Yeah.
So it looks like the light is getting Doppler shifted as if something is pulling it away. This is not actually what's happening, but you can imagine this as like when you have a car coming towards you and it's honking its horn, it goes, and then it like drops in frequency as it passes you and it starts moving away from you. And that's a Doppler shift.
Okay.
But the horn is not actually changing its physical frequency. It's just the way the waves are hitting your ear that are coming in rapidly as the car is moving towards you, and then as it moves away, they're coming in more slowly because the car is carrying away some of that velocity. This is not what happens with light, but you can think of it in the same way.
Okay, that was a very good analogy, by the way.
Yeah, so as things are further away, they seem to be moving away from us even faster, so things get redshifted even more, and you can measure that. So the neutrinos from the Big Bang, in this sense, are actually very low energy if we ever see them, but they're predicted to be very low energy today. And actually the only source of non-relativistic neutrinos, as far as we can guess, in today's world would be neutrinos from the Big Bang, and there are experiments actually trying to search for those neutrinos themselves.
Are they in the three places that you mentioned, or are they
No,
elsewhere?
this is a different experiment called Ptolemy, and it's not even, I don't think it's even under construction.
Oh, okay, so
Yeah,
it's
this is-
brand new.
This is brand new. This is a proposal. I'm not sure. Maybe I'm wrong. Again, like I'm also,
It's okay.
I'm only human. I make mistakes. So